think I'll get started. Find my stuff. Yeah, here we go. Heavenly Father, we thank you again for this day. I thank you for your many blessings. Just ask you to give us wisdom as we try to solve these systems of differential equations, and just help us all to learn something from these examples, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me begin with an example. So, as usual, we're going to try to solve a system of differential equations in here. This time, x prime is 2x minus y, and y prime is equal to 9x plus 2y. All right, so we want to find the general solution to this thing. All right. So the first order of business is to, basically convert it to a matrix problem, right? This is xy prime equals to 2, minus 1, 9, and 2 times xy, right? So my coefficient matrix A is that matrix, that 2 by 2. And so I need to look at what is the determinant of A minus lambda I. So I'm looking at the characteristic equation that's derived from taking the determinant of 2 minus lambda, minus 1, 9, and again 2 minus lambda. So we take that determinant, and that gives us a lambda minus 2 squared plus 9, right? And so if you set that equal to 0, I immediately can see that lambda is equal to 2 plus or minus 3i. Right? Because pretty much the characteristic equation has the square completed already, and so I can just see from that immediately the solution's complex, right? And it's plus or minus, 2 plus or minus 3i, right? Now, if you don't believe me, we could, of course, put an extra step in there if that would make you happier. All I'm, not showing you is that this says that lambda minus 2 squared is equal to minus 9. So then lambda minus 2 is plus or minus the square root of minus 9, which then gives me lambda is 2 plus or minus 3i. All right. So anyway, I don't feel the need to go through all that in here, because we should be able to recognize once we have a quadratic equation and the square is completed, we can read the solution directly off that. Okay, great. So we have complex eigenvalues. What do? We look for complex eigenvectors. Let's see how this works. So we're going to look at lambda is, we'll choose the plus for sake of specificity, 2 plus 3i, right? And we need to look at A minus parentheses 2 plus 3i times the identity matrix, that times my vector uv equals to 0. All right, so that's going to give me what? So I'm subtracting, 2 minus parentheses 2 plus 3i. It gets subtracted from the first one. I got a 9 down here. I got a minus 1 up here. And again, I've got a 2 minus parentheses 2 plus 3i. All right? So we can clean that up, right? That's just what? That's the 2's be canceling. We get minus 3i minus 1, 9, and minus 3i down here. All right? Now, at first glance, this is a little bit disconcerting because it looks like that we've got two equations, right? And it looks like these equations are distinct, right? To the untrained eye, perhaps those look like different equations, but are they? Are the two equations I'm looking at here, are they really distinct equations, or are they in fact the same equation in disguise? Well, let's try it out. So this first equation is minus 3iu minus v equals to 0. Multiply by what? What if we multiply by 3i? What does that give us? That, right? And then what's that? That's 9 times I squared, which is oh, that's not minus 3i squared. I'm a dummy. What do we have here? Duh. Minus 9i squared, right? Plus 3i times minus 3i is minus 9i squared, which is 9. 9. So 9u minus 3iv equals to 0. Now, why am I doing this? Does this help solve the problem? Not even a little. All right? I'm doing this to try to convince you that these two equations are in fact the same equation. And as such, it doesn't really matter which one we use. So as a point of order, if I'm freewheeling and careless, I'll just pick one and use it. And that's fine as long as I haven't made an arithmetic mistake, right? But if you do check that the equations are the same, that does give you a little bit of a confidence boost that you really have the right equation both places, right? So, I mean, do you need to do it? Not necessarily. Okay, so that said, I really like the first equation. The first equation says that v is equal to, well, minus 3iu, right? So let's use that one. So in case you somehow missed what I just said, all of this is just redundancy check. You know, you don't need. I pretty much never require you to do that. I do require you to find a correct eigenvector, though. So okay, so then, how about this? Maybe we should put u equal to. What do you think? May I suggest 1? Let's put u equal to 1. Then that tells me, so this is choose. I'm choosing u equals to 1. Once I make that choice, my v is what? It's minus 3i, right? So consequently, we find, let's call it z as a vector of t is equal to e to the 2 plus 3i times t times my uv vector, which is in this case, where was I? 1 and minus 3i. There you go. So if you study the arguments we made last time, you should find that those arguments apply equally well to complex valued functions as they do real valued functions, because we know e to the lambda t differentiates the same way whether lambda is real or complex, right? Just derivative of e to lambda t is lambda e to lambda t. That was the linchpin for proving that the eigensolution was a solution, and as such that math still holds here. But what's the rub? We find a what? A complex solution. And that's not what we want. Right? Let's say dr dt equals to ar. Here my r is, as usual, xy, right? So how do you find, what's the theory say? The theory says that there exists a real solution set, right? Two linearly independent real functions. How do I find them? What do you think they are? What did we do before when we had this? Make cosines and sines. Yeah, but more big picture, like 500 feet above, what are we looking down? We're just doing what? We're taking the complex solution and we want to find the real part and the imaginary part. Those are separately real solutions. So how do we find that? we need to actually put in the details of what this is. Well, this is e to the 2t, right? Leave that out front. You got yourself a cosine 3t plus I times the sine of 3t, right? Times what? Times the vector 1, 0, plus I times the vector 0, minus 3. All right? And if we multiply this out, what do we get? Well, we have like e to the 2t times what? Oh, well, on the one hand, we've got our cosine of 3t times 1, 0. And then I times I is what? I squared is minus 1, right? So I get minus the sine of 3t times the other vector, which was 0, minus 3. All right, that's my real part. And then plus I times e to the 2t, big parentheses. Then I get sine of 3t times my first vector, which was 1, 0, plus cosine of 3t times my second vector, which was 0, minus 3. So at this point, you can explicitly see what we have here. This piece is the real part of the complex solution. And everything except for the I over here is the imaginary part of the complex solution. And as such, that allows us to derive that my solution is, I guess I'll write it here. So we've got R of t is C1 e to the 2t. I'll leave that out front. And if I put those together, I've got like a cosine 3t and what, like plus 3 sine 3t for that one. I'm just adding it together to save myself some writing, okay? And then the other one, C2, e to the 2t times sine 3t for my top component. And downstairs I get a minus 3 cosine 3t over there. Now this right here, my friends, would be this is the vector, the real vector solution. If I wanted the scalar solution, what would it be? What would the scalar solution to this problem be? Nah, I had to erase something. Does anybody have any questions about the eigenvector calculation before I erase it? All right. The usual question is, why did you pick u equals to 1? The answer is, why not? Right? There's only one choice we could not make there, which would have been what? 0. The other question you guys will ask once you realize you have a question, which will happen, is why did you use the plus eigenvalue? Why not use minus? And the answer to that is, because I can. It wouldn't have made much difference. If I had, well, I'll show you the theory here in just a second, but let me write down the scalar. So like the actual solution to x and y is x is equal to c1 e to the 2t cosine 3t plus c2 e to the 2t sine 3t. All right, and y is equal to like c1 e to the 2t sine 3t. Wait a minute. 3. There's a 3 here, right? 3 c1 e to the 2t sine 3t and minus 3 c2 e to the 2t cosine 3t. So there you go. There's the real scalar solution. All right. I pretty much never ask for the complex solution in here, so you should almost always just assume I'm looking for the real solution as the answer. The complex thing is just a step towards that direction. Like it's an intermediate step. It's not the answer, right? We try to keep it real in here. So, except when we don't. But yes.
We can usually leave it in the vector solution.
Oh yeah, the vector solution is also a totally acceptable answer. I like that. I like that even more sometimes than, in fact, as much as I like this, I sometimes even like this. Like this over here actually is a totally legit solution to this kind of problem. If I just say find the solution in vector format, this also would have been totally good answer. Excuse me, no, wrong, there's an I here. So to make this a good answer, I would have had to do what? Erase this equals, and inject a C1 here, right? Erase this I should not be in the answer, but put a C2 here, right? Slap an R over here, and there you go. That's another way we could have written the general vector answer. There should not be an I in your answer. If there's an I in your answer, you need to poke it out. Just poke it. Poke it until it's gone. Put a C through it. Put a C. Yeah, okay. All right. So just a quick tour of how things work. So like if A is a real matrix, right, and A times U is equal to lambda U, where like U is equal to A plus IB, and lambda is equal to alpha plus I beta. All right? Then one of the things you can do with that equation is to take the complex conjugate of it. Now, A is a real matrix in my discussion here, right? So what happens with the complex conjugate of the real matrix? The answer is, well, nothing. All right, so, and so let me just do that here. So like the complex conjugate of this equation, right? I guess I'm using star for complex conjugate today. Sometimes I use a bar. It depends on which book I'm looking at or whatever. So I get A times U conjugate is equal to lambda conjugate U conjugate. Now the complex conjugate of U is A minus IB. Here I'm assuming that A and B are real vectors, okay? So what does this mean? Like, look at this equation. What does it say? That says that U conjugate is an eigenvector for A. It says it's an eigenvector with eigenvalue what? U conjugate, which by the way is A minus IB, is eigenvector of A with eigenvalue lambda star. What is that, by the way? That's alpha minus I beta. All right? So what I'm trying to just take a second to explain to you is the reason it's okay for us to just look at one of the eigenvalues in the complex case is because the other one, it doesn't have any new information in it. All right? Like the complex eigenvector that we found here, all right? This thing was A, and this thing was B. If I had used the, the complex conjugate, right? If I'd used the complex conjugate eigenvalue, I could have found the same complex eigenvector, except instead of having B, I would have had minus B, right? That's one potential scenario. Now the truth of the matter is it's much uglier than this, because that choice we made for U being 1, actually we could have made that any complex number, which means that there's a literal infinity of possible answers. It's quite horrible to grade. But usually you guys have pity on me and just use 1. I should like enforce it or something, I don't know. But yeah. Now, let's just talk about what we did in this previous example. Let's try to distill it into like a more general theorem, all right? So what I was just arguing is that z, which is equal to, e to the lambda t times u vector, right, is like a complex solution to dx dt equals to ax, right? It's a complex solution. But this is specifically e to the alpha t times cosine beta t plus I times the sine of beta t times, well, a vector plus I times b vector. Now this a and b vector is the notation of Nagel, Saff, and Snyder, which is technically our textbook. But I guess my notes have enough. But anyway, so this works out to cosine beta t times the a vector minus the sine beta t times the b vector, all right, plus I times e to the alpha t sine beta t times the a vector plus cosine beta t times the b vector. And so, like, the theorem is that, dr dt equals to ar has solutions, R1 and R2, where, this right here is R1, and again, without the I, is R2. And so if you don't want to go through this business we did of selecting the real and the imaginary part, and you just want to remember this theorem to write down the answer, you are free to do that. That's what I usually do. But of course I do understand where it came from, and you should too. It's good to understand. But it's also nice to have a formula, But if you look at what we did, that's what we did, right? You see it? I have like cosine A minus sine B for the first one, and I've got sine A plus cosine B for the second one. That's exactly the pattern that we had there. So this is the deal with the complex. Now again, if you and your friend work on the same problem and you get different answers, do not assume that either one of you is wrong. Because again, you could basically, here's the thing. So our eigenvector in this problem was, what was it? It was 1 minus 3i. I can literally take this and multiply by c plus id, and I would get, c plus id, and then down here, minus 3ic plus 3d. And this is like, general form of any lambda equals to 2 plus 3i eigenvector. So like, there are a stupid number of possible eigenvectors you could have found here. And they would make the solutions look a little bit different, but it really just amounts to a different, ultimately what's happening is we're just like changing the meaning of C1 and C2 in the answer. It's essentially just a different way of making contact with the initial conditions if you were to be given some. Once we're given initial conditions, the answer is unique, right? So if I really want to make my grading easier, I take one of these and I slap on, oh, by the way, at time 0, it's at the point 1, 2 or something, Right? Like if I say at time 0, it's at the point 1, 2, what's that do? What happens? Put in time 0, we get C1 from this, right? And we put down here, we get what? Minus 3C2, right? So therefore my C1 would be 1 and my C2 would be like minus 2/3. And whatever in the infinity of choices you made otherwise, the algebra would conspire as you fit the initial conditions in to give you back that same exact answer. That's what would happen if you chose a different eigenvector. again, it just corresponds to a different sort of labeling of initial conditions. Okay, so another problem, unless there's a question. Oh, oops. Okay. Aw, man. This board is really kind of trashy, honestly. All right, so the time has come for us to face the music of the 3x3 problem. All right? So you have been perhaps given the, well, anyway, I'll not make disparaging comments about other courses. I'm just going to say we're going to do a 3x3 in here. All right, let's see here. So, because we can, I mean, it does require a little bit more effort, obviously. This is the kind of speech I give right before I make some kind of terrible, horrible mistake in my work, right? So, here it is. We want to solve dr dt equals to AR, where A is equal to 2, 0, 0, minus 1, minus 4, minus 1, and 0, 5, and 2. All right, let's see if we can solve this one. So first order of business is to figure out the eigenvalues. So we want to look at the determinant of 2 minus lambda, 0, 0, minus 1, minus 4 minus lambda, minus 1, 0, 5, 2 minus lambda. All right, so I think pretty obviously we should expand on the top row, right? Like, so that gives me 2 minus lambda times the determinant of this piece right here. All right, and so that gives me 2 minus lambda times, well, I'm going to absorb the minus into that, so big parentheses here. Lambda minus 2 times lambda plus 4 plus 5, which is, I'm going to pull a minus out of that because it's just bothering me. Lambda minus 2, and this is giving me lambda squared. Minus 2 plus 4 is plus 2, so plus 2 lambda. Minus 8 plus 5 is minus 3. All right, so what we got here? Lambda minus 2 times lambda plus 3 times lambda minus 1, right? There you go. So what are the eigenvalues? We got 3 of them, right? And that's good because the theory here says that each eigenvalue gives you at least one eigenvector. And therefore, we're going to get the complete solution set here because we're going to have 3 eigenvectors and 3 eigensolutions. So that's good. That means we don't need anything more than this. All right? All right, so let's look at lambda equals to 2. Start with that one, yeah? So we got to do a minus 2i times, let's say, u1, which in this case is going to be 0, 0, 0, minus 1, minus a 6, minus 1, 0, 5, 0. And for now I use UVW for my disposable variables. Okay? And the question is, can we solve this? Now we've got 3 equations, a little bit trickier. We can't just pick one and work with it, right? We're going to have to actually think a little bit more here. But we don't have to think too much, right? Like if you have 221 under your belt, you know about like row reduction, or maybe you remember from high school if you're Dr. Sprano, et cetera, et cetera. Like you don't need row reduction for this kind of problem. You can just reason through it, right? Like the bottom row is very helpful. What's it say? This is inescapable. It says what? What's it say about the vector UVW? 5v equal to what? So therefore v is 0. Hold on to that one. That's helpful. Now, how about the first equation? First equation says 0 equals 0. Do we care about that? Not even a little. We're going to ignore that one. The middle equation then says what? Negative u.
Negative u minus 6v.
Yeah. So negative u minus w equals to 0 because, remember, we know v is equal to 0, so we can use that. We're solving all three equations at once. If we learn one of the equations demands v to be 0, use it. Simplifies the other equation. And then, oh, look at that. We got w is equal to minus u. All right. I think you know what I'm about to say next. We should set u equal to what? 1. Yay. So let u equals to 1, and that gives us eigenvector u1, 1, 0 for my v, and minus 1 for my w. There you go. All right. So there's my first eigenvector. Next up, what's my next eigenvalue? So like from this here, I'm seeing this up here, guys, tells me that lambda 1 is 2. My lambda 2, I'm going to use minus 3. My lambda 3, I'm going to set equal to 1. Just to be, I mean, that's just how I picked them. You can label them differently if you want to, but that's what I did. So lambda 1 was 2. Lambda 2, I said, was minus 3. All right, great. So I need to do a plus 3i times u2, which, by the way, is what? A plus 3i. So I've got myself a 5, 0, 0, minus 1, minus 1, minus 1, 0, a 5, like that, times UVW. Now this is a new UVW, right? These are disposable variables. I refresh those at each new eigenvalue, okay? So this UVW has no connection, not directly at least, with respect to my old UVW. All right, I did a core dump, memory erase, whatever you guys call it, I don't know. So fine. So there is this is, all right, there we go. So what happens here? First line gives me what? 5u. So we 5u is equal to 0. This time u is equal to 0. We're not going to be able to put u equal to 1 this time, right? U are 0. Now, and then we're up against what? Like minus v minus w equals to 0, or 5v plus 5w equals to 0. Same story, right? Same thing, same equation, right? The second and third equations are the same equation once you understand u is 0. So pick whichever one you like. I prefer the second one. And that gives me that w is equal to minus v. All right. I will now choose v equals to 1. Therefore, my u2 vector is going to be a 0, 1, minus 1. There's my second eigenvector. By the way, we can always check our answer by like going back to the matrix that we have and multiplying by the vector. If it actually is an eigenvector, we should get back a multiple of the same eigenvector, and the multiple should be the eigenvalue, right? Try it out. What happens when you take my 1, 0, minus 1 vector and multiply by a? What happens? You get 2, 0, and then minus 2, which is 2 times the vector, which is what we want because the eigenvalue is 2. Try out the third one. Try out the second one. What happens if you take a times u2? What do you get? Work it out while I'm erasing. If we did it right, we had better get what? We had better get minus 3 times the vector. Yeah. So I hope you can see that that is what happened. All right, one more eigenvector. What do we got here? So my remaining eigenvalue was 1. All right, so now I need to solve a minus I times u3. A minus I times u3. Right, so this is my lambda 3 equals to 1 eigenvalue. Now, A I can no longer read. So 1, 0, 0?
Yeah.
All right. Then I subtract 1. So I get minus 1, minus 1, minus 5, minus 1. And then 0, 5, 1, right? Again, my disposable UVW come back again, serve their purpose. So look, again, we've got u is equal to 0. So then the bottom two equations, right? Once you put u equal to 0, the second and the third equations are the same equation, right? So which one we can ever use whichever one. I'll use the third one. So I got 5v plus a w is equal to 0, which then tells me that w is minus 5v. So I will choose v equals to 1. And then that gives me my u3 vector is 0 for u, 1 for v, and minus 5. Now, why are we doing this? Well, last time we derived that if you have an eigenvector with an eigenvalue, that gives you an eigensolution to the problem. Put that together with the theory, we find thus, dr dt equals to ar has solution r of t is equal to c1 e to the lambda 1. Well, let me just write out. C1 e to the, what was lambda 1? Lambda 1 was 2. So e to the 2t. And my first eigenvector, what was it? It was
1, 0, negative 1.
1, 0, negative 1. Okay, cool. Plus c2 e to the minus 3t. My second eigenvector was 0, 1, minus 1. All right. And then plus c3 e to the, t times this 0, 1, minus 5. And there you go. That is the solution to this system. Yep.
Is this faster than solving each individual equation?
Well, I don't know. I think so. Usually. Here we've got dx dt is equal to 0. We've got dx dt minus dx dt minus 5 times dy dt minus dz dt is equal to 0, and then 5 dy dt plus dz dt is equal to 0. So this is what it would look like if you were to face it just directly. Yeah, I mean, this is not that ugly of a problem. If you can see your way through it, it's probably faster to solve it by hand, but I will ask you to solve it by the method of eigenvectors, so it's a somewhat academic question. But I mean, I guess my response is somewhat academic, but but yeah, I mean, I have had one student in the hundreds of engineers that I've ever taught this class who has been successful in avoiding the eigenvector method and just solving them directly. Just one. I don't recommend that, though. I really don't. Because partly, not only do I not recommend it, I don't allow it. You need to learn the eigenvector method. It's important. But yeah, I mean, this problem, x is a constant, and you can kind of like maybe go from there, if I'm not wrong. Oh, wait a minute. I'm not even looking at the right equation, though. This is not it. I'm just looking at that. I'm an idiot. It was worse. It was this, right? So I had, I'm an idiot. It's not dx dt equals 0. It's dx dt equals to 2x, right? It was dx dt equals to 2x. It was, good grief. dy dt equals to, minus x plus 4y minus z, and dz. This is the equation. This is the differential equation we're solving, not the one I wrote. Right? I'm an idiot. 5y plus 2z. Right? So, admittedly, yeah, you can solve this one. That's a gift. Right? That the solution to that is x is equal to e to the 2t, because lambda equals to 2 is the characteristic equation. Great. Then you'd need to plug that in here, and you'd still have the y and the z equations all intertwangled. But the niceness of what we just did is reflected in the niceness of how the characteristic polynomial worked out up here. The fact that when we calculated the determinant of the 3 by 3, it came ready, it factored itself. That doesn't happen generally. Usually, you have to think a little bit harder about how that 3 by 3 determinant sorts out. Let's see if I can find one of those. Yeah, okay, this one's probably good. If I have time. Ooh, debatable. Actually, I'll project this one rather than write it out. One of the things I wanted to say here before I leave this example is from this, we can build a fundamental solution matrix. Fundamental solution matrix is what? It's a matrix of solutions, right? Where the solutions are linearly independent. So like I can do, the first one would be like, e to the 2t, 0, minus e to the 2t for my first column. Second column, 0, e to the minus 3t, minus e to the minus 3t down there. And then finally 0, e to the t, and minus 5 e to the t. So this, by the way, is a fundamental solution matrix that we can build from our 3 linearly independent solutions. I mention this in part because we need this idea to build the particular solution when we get to it a little bit later. All right? And fundamental solution matrices are of their own interest. So anytime you can find a general solution, you can put it all together and make a fundamental solution matrix like this. All right? Anyway, let me show you something. So I wanted to show you guys example 4.4.10, I think. 4.410, which is on my page 148. If I can find it.
What was the example again?
What did I say? 4.410 on page 148. If I can find the cable, we'll be in business. You can do it. Yes. All right. Do you like my art? It took me like a whole prompt to get that. So Where are we? So here-ish. Let's see here. I worked through a couple of these with you guys already. We just did this one. We just did example 4.48. Let's see here. So this one's interesting. All right. This one's interesting. So here, oh man, well I don't show the rats. I was hoping I'd show the details. I guess I haven't. But to actually work this out, it's not immediately obvious that it's that, right? Like I would have, well, we have a minute. Let me show you what's involved, right? So we're looking at the determinant of, we got to do 2 minus lambda, 1, what's the top, 0, right? And then 0, 2 minus lambda, is that a 0 again?
Yes.
0. And then 1 minus 1. And then 3 minus lambda. All right. Oh, see, this one's nice. This one's too nice. Well, let me not make it nice. Let me just show you what happens if you're not clever. So this is 2 minus lambda times the determinant of this business, right? Which is 2 minus lambda, 0, minus 1, 3 minus lambda, right? And then I do minus 1 times the determinant of this piece and that piece, right? Which is 0, 1. Oh, I guess this problem's just nice. There's a reason I didn't show the steps. It's because it's kind of super easy. So that's that second determinant is 0, right? So the first one's the only one that actually kind of comes into play here. Yeah, and so lo and behold, we get the characteristic equation that we got there, right? Because this just gives me, like the next step is the answer, 2 minus lambda squared times 3 minus lambda. All right. Now, so notice here that something interesting happens in this example. So like we go look at the, so first of all, the eigenvalue 2 is repeated, all right? In the previous example that the eigenvalue 2 is repeated, we found 2 eigenvectors. But this one, not the case. If we look at a minus 2i, that gives us this, which actually just gives us 1 eigenvector. Put u equal to 1. 1, 0, minus 1 is the token eigenvector. That's all I can get. And then I look at eigenvalue 3, and I get another eigenvector, right? So I only get these two eigensolutions. What gives? It's a 3 by 3 problem. I can't solve it with eigenvectors, right? So there's something missing to this story we haven't covered yet, right? So there's something other than eigensolutions that we need to learn about. So that's one of the points. The other point, while I have this out, is that you guys should know about this. I personally like you guys can use MATLAB or whatever, but I like this a lot. So like, for example, pick any matrix you like. 1, 1, 1, I don't know, 2, 4, 6, 7, 6, 7, there. Calculate the eigenvalues. There you go. Check it out, yo. The eigenvalues are, there's a 12.5, and then there's complex eigenvalues. And there is a numerical approximation to the eigenvector, and there's a numerical approximation to the complex eigenvector. And so this is super helpful. If you're checking your homework, you want to double check, did I get the eigenvectors right? Just use this website, right? I'll make an announcement about this. It's linked in my linear algebra class, but not in here. So anyway, I will shut up. See you guys later.